Welcome to the Deep Dive, where we dig into a huge stack of complex research and, well, we pull out the essential knowledge you really need.
And today's topic is, it's a heavy one.
It is. Our mission today is to plunge deep into the neurobiology of methamphetamine use. We've gathered some truly cutting-edge sources that map out the structural damage, the functional deficits, and some really revolutionary biomarkers that researchers are using to understand methamphetamine use disorder.
Which we'll just call MUD for short.
Great, MUD.
And this isn't just about behavior, this is hard science. We're talking about brain imaging, MRI, PE scans, EEG, that gives us a window, a really clear view of the brain under siege.
And the context here is, it's immediately sobering. These researchers, when they talk about long-term, high-quantity ME use, they equate the physical damage to a traumatic brain injury, a TBI.
Yeah, and that's a very deliberate comparison. It's not just a metaphor. It signals that MUD is a severe neuropsychiatric disease. The damage isn't just chemical or, temporary. It's physical. It involves this profound restructuring of the brain, from huge gray matter structures right down to the microscopic wiring of a single neuron. It tells you we have to treat this as a deep biological problem.
Okay, so let's unpack this, starting right at the hardware level. If we could look inside the brain of an abstinent MA user, what's the very first thing these scans pick up?
You have to start with the brain's core communication systems. The research is clear. Chronic MA use is directly neurotoxic.
Meaning it poisons the neurons.
It poisons the neurons, specifically in the systems that manage dopamine and serotonin. MA fundamentally attacks the very infrastructure that's supposed to manage those critical signals.
And what does that attack? What does that damage actually look like when you measure it?
It looks like a massive reduction in the recycling machinery for dopamine. We're talking about something called the dopamine transporter, or DET.
DET. Okay, what's its job?
Think of DET as the cleanup crew. It's the essential mechanism that neurons use to pull dopamine back out of the synapse after a signal has been sent.
So if the cleanup crew is gone, what happens?
The whole system just gets gummed up. And the cells themselves, they start to die off from the toxicity. The data shows abstinent MA users have these really substantial reductions in DAT density in a part of the brain called the striatum.
How substantial are we talking?
Well, the sources cite reductions as high as 27.8% in one area, the caudate, and 21.1% in another, the putamen.
Almost 28%. Imagine losing more than a quarter of your brain's essential dopamine handling capacity. That sounds devastating. And it makes me think about long-term risk. Does that point toward other conditions down the line?
It raises a huge red flag, a serious one. The defining feature of Parkinson's disease is the loss of dopamine terminals. So when you see these kinds of reductions, it raises the very real possibility that MA users are at an increased risk for developing Parkinsonism as they age.
But the brain is resilient, right?
Yeah.
Is that damage permanent, or does it try to repair that lost infrastructure?
The brain absolutely fights back. And recovery is strongly associated with how long someone remains abstinent.
So time helps.
Time is critical. One key longitudinal study, they used PET scans to track users over time, showed a partial recovery in those DAT levels. Specifically, a 19% increase in the caudate after about 12 to 17 months of abstinence.
So the cleanup crew starts to trickle back in. That's hopeful.
It is hopeful, but there's a crucial caveat here.
I was afraid of that. Structure improves, but function might not keep up.
Exactly. While the biological markers, the DAT levels, show that measurable improvement, the cognitive tests they ran alongside them, they did not necessarily show a full functional recovery. The road is getting repaved, but the traffic still isn't moving at full speed.
Okay, so the infrastructure gets a partial fix, but performance might take years. Or maybe it never quite gets back to pre-use levels.
That's the concern.
So beyond the dopamine system, what about the main physical structures? The gray matter, where the brain cells live, and the white matter, the communication highways.
We see a dual impact there. Pervasive. For gray matter, the sources consistently report reduced volume and a thinning of the cortex, that critical outer layer.
And where is this thinning happening?
It's hitting the areas responsible for our highest order functions. The insula, the frontal lobes, especially the prefrontal cortex and limbic areas like the hippocampus. In some cases, they're reporting actual atrophy. Shrinkage.
That makes a scary amount of sense.
Yeah.
The prefrontal cortex is our CEO, our planner. The hippocampus is ground zero for memory. If those shrink, you'd expect those core functions to suffer.
You would. And we do see that. But there's a surprisingly complex finding, especially in younger users.
You're talking about that study with the adolescents with MUD. What did they find with the white matter?
Right. So they compared young people with MUD to a control group of athletes. And the MUD group had the expected reduction in gray matter, about 5% lower. But, and this is the strange part, they actually showed 10% greater total white matter volume.
Wait, greater? That feels like the opposite of damage. Why would the communication highways be bigger?
It's not entirely clear. It really speaks to the complexity of the pathology. It could be a different stage of injury or some kind of compensatory mechanism or maybe an issue with myelination. But we do know that long-term MA abuse is definitely not good for white matter health.
Okay, so how do we know that?
Because we see damage to glial cells, which leads to something called decreased gliogenesis, basically, the production of new support cells stalls out, especially in that prefrontal cortex.
And the glial cells are the support system for the neurons. What happens when they're damaged?
You start to see signs of wear and tear. On scans, these show up as white matter hyperintensities, or WMH.
Hold on, WMH, aren't those the same little spots you sometimes hear about in brain scans of older people or people with high blood pressure?
Exactly the same. They signal microvascular damage and demyelination damage to the protective coating around the axons. They're these little visible indicators of chronic injury and inflammation happening in those white matter highways.
Which brings us to where this gets really interesting. The link between that cellular damage and the big picture, inflammation and accelerated aging. Is the brain basically attacking itself?
In a way, yes. Chronic MA exposure triggers significant measurable neuroinflammation. You can see it through increased microglial activation. The microglia are the brain's resident immune cells.
And they go into overdrive.
They go into overdrive, especially in the striatum and the cortex, but it gets even more specific in the frontal lobe.
What happens there?
Chronic MA use causes a significant loss of dendrites and dendritic spines. Those are the receiving antennas of the neuron. The little communication points. When you lose them, the cell loses its ability to talk to other cells effectively.
So the very branches that neurons use to form networks are just shriveling up.
They are, and we can confirm this is a massive, sustained inflammatory process because of the cellular markers.
And this is where the data just gets dramatic.
It really does. That dendritic loss in the frontal lobe correlated directly with a massive upregulation of specific immune signals, type I interferons. They were upregulated by an astonishing 12.6-fold to 16-fold.
16-fold. That's not just inflammation. That sounds like a biological 5-alarm fire. The brain's systemic alarm is just ringing constantly, 16 times louder than normal.
It's a clear indicator of severe, catastrophic neuroinflammation that isn't being resolved. And that links directly back to that idea of accelerated aging. When you have that level of chronic, unresolved inflammation, you start to see markers you'd normally only find in a much older brain.
So all that cumulative damage is effectively making the brain age faster.
That's the hypothesis the data supports. Things like a higher burden of those WMH spots we talked about, or larger volumes of the choroid plexus. These are things we'd expect to see in old age, but we're seeing them in people with MUD much earlier. The brain's structure is just prematurely degraded.
Let's pivot to performance then. What does this damaged, inflamed hardware actually mean functionally?
It means you get these significant, persistent cognitive deficits. The functions that suffer the most are the ones governed by that damaged prefrontal cortex. Attention, working memory, inhibitory control, decision-making, self-regulation, all the big ones.
This speaks right to the core struggle of addiction, doesn't it? That battle between immediate desire and logical control.
Absolutely. And you can see the physiological proof of that link. Studies show that frontal lobe hypometabolism, which just means low glucose use, the area isn't getting enough energy, is directly associated with worse performance on executive function tests.
The critical thinking machine is just running low on fuel.
It is. And the brain's wiring reflects this internal battle. The whole system is dysregulated. Functional MRI studies describe it as an inefficiency in frontoparietal circuitry.
Inefficiency? What does that mean in a biological sense? Is it like a computer running too many background programs?
That's a perfect analogy. In a healthy brain, you see strong neural activation only during hard tasks. It conserves resources. But MA users show high levels of activation during both easy and hard tasks.
So they're over-engaging.
Massively. They're running their internal CPU at 100% just to check email. It's exhausting, it burns energy, and it's completely unsustainable.
Wow.
On top of that, resting state studies show the reward network is basically stuck in the on position, which correlates directly with cognitive impulsivity.
That hyperactive reward system, that impulsivity, that has to connect to craving. The sources say craving isn't just a feeling, it's a powerful predictor of relapse.
A huge predictor. It can double the odds of future drug use, and we can now measure that craving reaction objectively.
Okay, so let's shift to that cutting-edge tech. Using EEG as a biomarker, what electrical signatures pop up?
So in a resting state, just sitting there, abstinent MA users often show abnormal EEG patterns, specifically increased power in the slow waves like delta and theta bands.
And what does that mean?
Well, increased theta power correlated with worse performance on reaction time tasks and lower working memory accuracy. It suggests a kind of persistent baseline cognitive impairment.
So the slow waves signal damage and poor performance at baseline. What happens when you actually trigger a craving?
That's where the high-frequency waves come in. When MUD patients are exposed to drug cues, say, in a virtual reality environment, their brains show a significant localized spike in high-frequency gamma power.
And where does this spike happen?
Primarily recorded by frontal electrodes, right over those areas we know are structurally damaged.
Linking the subjective feeling of craving to an objective gamma spike, that feels revolutionary. That could totally change how we measure addiction, right?
It's a game changer. It suggests gamma power could be an objective marker of cue-induced craving, a neurological smoking gun for relapse risk that's totally independent of what a person tells you they're feeling.
And do we know the specific circuit that craving signal is using?
Animal models point to a specific pathway of neurons running from the anterior cingulate cortex, the ACC, to the colostrum, or CLA. Targeting that specific pathway could be a huge key for future treatments.
Before we get to solutions, there's a link to psychosis. Some users develop meth-induced psychotic disorder, MPD. Does EEG show a signature for that too?
It does. The ratio of slow-wave delta to mid-range alpha activity is significantly higher in MPD patients. It's indicative of an inappropriate arousal state, which likely contributes to the disorganized thinking in psychosis.
Okay, so interventions. Given this deep TBI level damage, what are the immediate hurdles for treatment?
The biggest hurdle is the lack of any FDA-approved medications specifically for MUD. Treatment relies almost entirely on behavioral therapies.
And other drugs have been tried and failed.
They have. One large trial found that the common antidepressant sertraline, Zoloft, was not only ineffective, but it might have even decreased the likelihood of someone maintaining abstinence.
That's worrying. So if medication is off the table for now, how can behavioral strategies possibly compete with that profound biological drive? I'm thinking of contingency management or CM.
CM is often described as a brilliant biological workaround. It gives clients immediate, tangible rewards for meeting goals, like a clean drug test. One of the experts in our sources described it as giving the damaged brain a necessary, healthy hit of dopamine.
So it's basically a physiological bridge to recovery.
That's the perfect metaphor. It uses a healthy, predictable source of dopamine to start retraining that hijacked reward pathway. It provides reinforcement that's strong enough to compete with the drug memory, and that gives the damaged prefrontal cortex time to heal and re-engage.
What else is emerging? I know there are ideas around neuromodulation and even lifestyle changes.
Exercise shows great promise. One study combined neurofeedback, or NFB, with swimming. That combination was really effective in normalizing some of those EEG changes and significantly reducing craving scores.
So the combination is key.
It seems to create a synergy. NFB alone is only rated as probably efficacious, but adding exercise forces the brain to adapt in a positive way.
And what about directly manipulating the brain with tools like TMS or even deep brain stimulation?
Here we have to be so careful. These circuits are incredibly delicate. A preliminary study tried to use low-frequency TMS on the prefrontal cortex to reduce craving. The result was the complete opposite of what they wanted. It actually transiently increased cue-induced craving.
Wow. That's a powerful reminder of how easy it is to throw a complex system even further out of balance.
It just underscores the complexity, which is why more drastic measures like deep brain stimulation, DBS, which involves implanting electrodes, well, that remains a very complex, high-risk frontier.
This has been an incredibly intense deep dive. To summarize for you listening, methamphetamine profoundly alters both the brain structure and its function. We're talking TBI level damage, gray and white matter loss, catastrophic neuroinflammation, and a depleted dopamine system.
And functionally, that shows up as inefficient, overactive circuits, broken executive control, and these powerful, measurable EEG markers that can actually pinpoint craving.
But, and this is the hopeful part, the research also highlights the brain's incredible potential to heal and adapt.
Right, which leads us to a final provocative thought for you to consider. We know that positive changes, like an increase in gray matter volume, correlate with longer abstinence. We also now have these high-fidelity biomarkers, like that clear spike in gamma power when a craving is triggered.
So if our understanding of those biomarkers gets sensitive enough to monitor those changes in real time, what's next?
How close are we to a truly personalized treatment model? A future where we can look at an individual's neurophysiological fingerprint and intervene not just days before a relapse, but milliseconds before the craving becomes irreversible.
Using real-time data to predict and maybe even prevent that moment of relapse.
Exactly, before the person even consciously registers the craving. That computational approach, using your brain's own electrical signals to guide your recovery, that is the immediate, vital frontier.
An incredible and hopeful frontier. Thank you for guiding us through this. It's challenging material, but so important.
Sure.
And to you, the listener, thank you for joining the deep dive. We'll see you next time.